Hi, Keith Van Wimmer of VanTech Consulting. This is a continuation. This is part 2 of Understanding Loss Budgets. So in the first part, if you haven't already viewed that, you might want to take a look at that. That goes over some of the parameters that we're going to be using. Some of the parameters we're going to be using. So this sheet is available for download. I'll put it down in the comment section, add some links there. So this guy here is the standards as far as all the components that we have, splices, mechanical splices, connectors, splitters. Actually, splitters aren't on here, but if you're interested in that, let me know and I'll get you a chart for that. But everything that we put into a fiber optic network, anything that we insert into there has an allowable loss that is associated with it for all the components. So we're going to be focusing on the green sections here, or I'm sorry, on the red sections, which are the international standards, ITU standards, and the IEC, so on and so forth. So before we go any further, if you are a current subscriber, we'd like to thank you for your support. If you're a new visitor to the channel and this is your first time here, we'd appreciate it if you would consider hitting the subscribe and ringing the bell. We have our lab here. We have a spool of fiber here. This is actually 25,000 meters, so 25.2 kilometers. We have some launch bags here that are 1,000. We have some fiber coils here. So the other thing we have is these little 4-port splitters. Now, these are the same splitters that would be used in a PON network, not the same package. They're a little more complex, but this is a 16-port splitter, and again, same thing. They just put it in different container to put it into the cabinets and so on and so forth. But the technology, it's a planar splitter, so that is pretty standard. We're just going to do our calculations, and then we're going to do simple measurements using light source. So this is a laser light source, 1310, 1550, and then we're going to use a power meter. Up here we have an OTDR. We could use that. That's acceptable by the ITU standards to use for testing and loss testing. Sometimes the OTDRs have an actual power meter sitting on them, so you can use that. Again, we're just trying to get across the point of doing the calculation first, measuring it, and seeing how the measured one comes out compared to the calculation. All right, and so theoretically, since all the calculations are done at absolute maximum values that are allowed by standards, everything should be under that, meaning that we should be less than our calculation. If at any point in time you do your calculation and you're over, and I'm not talking 1/10 of a dB or something, we can explain that, but if you're a dB or dB and a half or 2 dB over your calculation, you have an issue in the network. This guy here will tell you if you have a problem just because it's going to give you a higher reading, but the only way you're going to find the location of it other than kind of hunting pecking is using an OTDR. So this not only will tell you what the fault is, but where the fault is. Okay, so Swiss Army knife of testing. Again, if you want to see anything that I'm talking about, OTDR, more information on that, launch bags, splitters, all this fun stuff, just let me know. Put something down in the comments, let us know, and we'll see if we can get a video out. Let's set up our first scenario. So the first thing we're going to talk about here real quick is just some rules. So this light source, I have it on continuous wave. It launches out at a -7. If you meter it, it's going to be -7.2, 0.3 dBm. All right. What it says here isn't really important. What we're going to do is we're going to actually measure it. So we have our meter set up at 1550. If you have this number incorrect, your readings are going to be skewed, okay? The other thing that we want to do is we're going to go in here and we're going to change it over. If you look up here, we can change that from dB, which means it's a relative measurement, which we're not going to use that. The deal with the dB is when you're using that relative measurement, you literally reference out this chord, okay? And once you reference out that chord, if you forget to re-reference the next time you test, that reference will remain in here. So let's say that we took out 2 dB just for grins. And then the next time you go and measure, it's going to take 2 dB off your measurement again. So again, I encourage you to stick with dBm. So the first thing we're going to do is we're going to plug this into our power meter. We're going to take a measurement, a base measurement on our light coming out in dBm. So this is an absolute value. So our laser right now is putting out neg 7.32. So I'm going to go ahead and jot that down. 7.32 dBm. That's a neg. Okay, so we got 25 kilometers up here of fiber, 25.2 kilometers. So based on 22 or 25 times the .3 should come out to around 7.5 dB of loss, right? So you can check my math on that, but it's close. So 7.5 is the number that we're looking at. So 7.5 dB of loss attenuation in our fiber. So the next thing we're going to do is we're going to connect up our connectors here. We're going to plug our spool into this, and we got 12.63. Once you subtract that 7.32, the launch value, right, was a negative, so that comes off of our negative 12.63, that gives us 5.31. So our calculated loss in this, without the single connector over here, because we did null out one, so we still have one connector that's providing a little bit of loss, but we came out with 7.5 dB. So again, we're at 5 and change, 5.31, and we're well within our calculation. Okay, so this cable, the fiber, it's good. All right. So just as a side note, if we wanted to check again, just to be sure that we don't have any macro bends or anything, what we can do is we can pop this over to our 1310 and then change our light wave to 1310. And that gives us a neg 15.93. One of the things that, that you need to make sure you do as well is measure your output power again. So it says again that 1310 is launching out at -7, -735, so we're good there. So there we go. So 1596, real quick, if we did our calculations at 25, we'll just do it 25 times 0.4, that's 10 dB. So the 1596 minus the 735 is 867, 8.67 dB. So again, well within our 10 dB of expected or allowable loss. If there was a macro bend, our 1310 would read correctly, our 1550 would read higher. Now, on this scenario, because this fiber is only losing 0.187, I think it is what I measured on this for its attenuation rate, it's well below. So you could theoretically still have, even though we're testing and everything is good, you could still theoretically have a macro bend in that fiber, losing 0.5 dB, even as much as 1 dB. All right. So again, the only way that you find macro bends is using an OTDR to shoot 1310, 1550. That will identify the macro bend on your trace. But for now, as far as we're concerned, power meter and light source, everything's good. We can move on. Okay, so here we go with our second scenario. A little more complex. Not so much that it's more complex, there's just more things to think about and to add. Okay, we have more components. So we're starting off with our light source here. We come out with our test cable, and we've got one mated pair of connectors here. So we come through our 25 kilometers of fiber, 25.25, and we go into a pond splitter. So this is another mated connector. We come out of the pond splitter on another mated connector, all right? And then we go into 1 kilometer of fiber and then into our power meter. So we've got 1, 2, 3 mated connectors at 0.5 each. We have a pond splitter, so the pond splitter is 2 splits. So it's 3 dB of drop per split. So you have 50% of the light going on each leg for a two-way split. And that gets cut in half when you go to 4. So you got 25% remaining light here and 25% here. So that's 2, 4. That gives us 6 dB of drop there. So we have 1.5 dB on our connectors, 6 dB on our splitter. We have our 26.25 kilometers of fiber, and that's 7.87. So if we add all of that together, we should come up with our estimated loss. So according to my calculations, we come out with 1537. So I'm going to jot that down, 1537 dB. So again, we're launching out of the 7.3, and then we have a 2027. Take our 2027, we subtract our 735 for our launch. That leaves us with 1292. That's how much light we're actually losing. According to our calculations, our maximum allowable loss is the 1537, which gives us about 2.5 dB, 2.45 dB of headroom that we have to play with. So again, this tells us that everything is within specification as far as the power meter goes. Now, once again, the only true way we know exactly what's happening in that fiber is to use the OTDR and get an OTDR shot. But this will work for calculating out and giving you an initial idea of whether or not your circuit's going to work. So we hope you find these videos useful, get some kind of takeaway from them. This isn't overly complex, and yet there's a lot of things that you have to think about. So hint is, do a drawing of your network as best as you can to represent it. Just a line drawing, show a connector, show the splitters, how much fiber, and that way you're making sure that you're getting all the contributors calculated in. We'd like to thank you for subscribing. If you're not currently subscribed, we ask that you consider mashing that subscribe button and the bell. So until next time, be safe, and thanks for watching.